The speed of sound is the distance traveled per unit of time by a sound wave propagating through an elastic medium. In dry air at 20 degrees Celsius, the speed of sound is 343 meters per second. This is 1,234 kilometers per hour, or about a kilometer in 3 seconds or a mile in 5 seconds. In fluid dynamics, the speed of sound in a fluid medium is used as a relative measure of speed itself. The speed of an object divided by the speed of sound in the fluid is called the Mach number. Objects moving at speeds greater than Mach 1 are traveling at supersonic speeds. The speed of sound in an ideal gas is independent of frequency, but does vary slightly with frequency in a real gas. It is proportional to the square root of the absolute temperature, but is independent of pressure or density for a given ideal gas. Sound speed in air varies slightly with pressure only because air is not quite an ideal gas. Although the speed of sound is expressed in terms of a ratio of both density and pressure, these quantities cancel in ideal gases at any given temperature, composition, and heat capacity. This leads to a velocity formula for ideal gases which includes only the latter independent variables. In common everyday speech, speed of sound refers to the speed of sound waves in air. However, the speed of sound varies from substance to substance. Sound travels faster in liquids and non-porous solids than it does in air. It travels about 4.3 times as fast in water, and nearly 15 times as fast in iron, as in air at 20 degrees Celsius. Sound waves in solids are composed of compression waves, but there is also a different type of sound wave called a shear wave, which occurs only in solids. These different types of waves in solids usually travel at different speeds, as exhibited in seismology. The speed of a compression sound wave in solids is determined by the medium's compressibility, shear modulus and density. The speed of shear waves is determined only by the solid material's shear modulus and density. Basic concept: the transmission of sound can be illustrated by using a toy model consisting of an array of balls interconnected by springs. For real material, the balls represent molecules and the springs represent the bonds between them. Sound passes through the model by compressing and expanding the springs, transmitting energy to neighboring balls, which transmit energy to their springs, and so on. The speed of sound through the model depends on the stiffness of the springs. Effects like dispersion and reflection can also be understood using this model. In a real material, the stiffness of the springs is called the elastic modulus, and the mass corresponds to the density. All other things being equal, sound will travel more slowly in spongy materials, and faster in stiffer ones. For instance, sound will travel 1.59 times faster in nickel than in bronze, due to the greater stiffness of nickel at about the same density. Similarly, sound travels about 1.41 times faster in light hydrogen gas than in heavy hydrogen gas, since deuterium has similar properties but twice the density. At the same time, compression-type sound will travel faster in solids than in liquids, and faster in liquids than in gases, because the solids are more difficult to compress than liquids, while liquids in turn are more difficult to compress than gases. Some textbooks mistakenly state that the speed of sound increases with increasing density. This is usually illustrated by presenting data for 3 materials, such as air, water and steel, which also have vastly different compressibilities which more than make up for the density differences. An illustrative example of the two effects is that sound travels only 4.3 times faster in water than air, despite enormous differences in compressibility of the two media. The reason is that the larger density of water, which works to slow sound in water relative to air, nearly makes up for the compressibility differences in the two media. Compression and shear waves. In a gas or liquid, sound consists of compression waves. In solids, waves propagate as 2 different types. A longitudinal wave is associated with compression and decompression in the direction of travel, which is the same process as all sound waves in gases and liquids. A transverse wave, called a shear wave in solids, is due to elastic deformation of the medium perpendicular to the direction of wave travel. The direction of shear deformation is called the polarization of this type of wave. In general, transverse waves occur as a pair of orthogonal polarizations. These different waves may have different speeds at the same frequency. Therefore, they arrive at an observer at different times, an extreme example being an earthquake, where sharp compression waves arrive first, and rocking transverse waves seconds later. The speed of a compression wave in fluid is determined by the medium's compressibility and density. In solids, the compression waves are analogous to those in fluids, depending on compressibility, density, and the additional factor of shear modulus. The speed of shear waves, which can occur only in solids, is determined simply by the solid material's shear modulus and density. Equations. In general, the speed of sound c is given by the Newton-Laplace equation, where k is a coefficient of stiffness, the bulk modulus is the density, thus the speed of sound increases with the stiffness of the material, and decreases with the density. For ideal gases, the bulk modulus P is simply the gas pressure multiplied by the adiabatic index. For general equations of state, if classical mechanics is used, the speed of sound is given by where is the pressure and is the density, and the derivative is taken adiabatically, that is, at constant entropy per particle. If relativistic effects are important, the speed of sound is calculated from the relativistic Euler equations. In a non-dispersive medium, sound speed is independent of sound frequency, so the speeds of energy transport and sound propagation are the same for all sound frequencies. For audible sounds, the mixture of oxygen and nitrogen constitutes a non-dispersive medium. However, air does contain a small amount of CO2, which is a dispersive medium, and it introduces dispersion to air at ultrasonic frequencies. In a dispersive medium, sound speed is a function of sound frequency, through the dispersion relation. The spatial and temporal distribution of a propagating disturbance will continually change. Each frequency component propagates at its own phase velocity, while the energy of the disturbance propagates at the group velocity. The same phenomenon occurs with light waves. See optical dispersion for a description. Dependence on the properties of the medium. The speed of sound is variable and depends on the properties of the substance through which the wave is traveling. In solids, the speed of transverse waves depend on the shear deformation under shear stress, and the density of the medium. Longitudinal waves in solids depend on the same two factors with the addition of a dependence on compressibility. In fluids, only the medium's compressibility and density are the important factors, since fluids do not tolerate shear stresses. In heterogeneous fluids, such as a liquid filled with gas bubbles, the density of the liquid and the compressibility of the gas affect the speed of sound in an additive manner, as demonstrated in the hot chocolate effect. In gases, adiabatic compressibility is directly related to pressure through the heat capacity ratio, and pressure and density are inversely related at a given temperature and composition, thus making only the latter independent properties important. In low molecular weight gases, such as helium, sound propagates faster compared to heavier gases, such as xenon. For a given ideal gas, the sound speed depends only on its temperature. At a constant temperature, the ideal gas pressure has no effect on the speed of sound, because pressure and density have equal but opposite effects on the speed of sound, and the two contributions cancel out exactly. In a similar way, compression waves in solids depend both on compressibility and density just as in liquids but in gases the density contributes to the compressibility in such a way that some part of each attribute factors out, leaving only a dependence on temperature, molecular weight, and heat capacity ratio. Thus, for a single given gas and over a small temperature range, the speed of sound becomes dependent on only the temperature of the gas. In non-ideal gases, such as a van der Waals gas, the proportionality is not exact, and there is a slight dependence of sound velocity on the gas pressure. Humidity has a small but measurable effect on sound speed, because oxygen and nitrogen molecules of the air are replaced by lighter molecules of water. This is a simple mixing effect. Altitude variation and implications for atmospheric acoustics. In the Earth's atmosphere, the chief factor affecting the speed of sound is the temperature. For a given ideal gas with constant heat capacity and composition, sound speed is dependent solely upon temperature. See details below. In such an ideal case, the effects of decreased density and decreased pressure of altitude cancel each other out, save for the residual effect of temperature. Since temperature decreases with increasing altitude up to 11 km, sound is refracted upward, away from listeners on the ground, creating an acoustic shadow at some distance from the source. The decrease of the sound speed with height is referred to as a negative sound speed gradient. However, there are variations in this trend above 11 km. In particular, in the stratosphere above about 20 km, the speed of sound increases with height, due to an increase in temperature from heating within the ozone layer. This produces a positive sound speed gradient in this region. Still another region of positive gradient occurs at very high altitudes, in the aptly named thermosphere above 90 km. Practical formula for dry air. The approximate speed of sound in dry air, in meters per second, at temperatures near 0 degrees Celsius, can be calculated from. Where is the temperature in degrees Celsius? This equation is derived from the first two terms of the Taylor expansion of the following more accurate equation. Dividing the first part, and multiplying the second part, on the right-hand side, by gives the exactly equivalent form. The value of 331.3 ams, which represents the speed at 0 degrees Celsius, is based on theoretical values of the heat capacity ratio, as well as on the fact that at 1 atmosphere's real air is very well described by the ideal gas approximation. Commonly found values for the speed of sound at 0 degrees Celsius may vary from 331.2 to 331.6 due to the assumptions made when it is calculated. If ideal gas is assumed to be 7/5 equals 1.4 exactly, the 0 degrees Celsius speed is calculated to be 331.3 ams, the coefficient used above. This equation is correct to a much wider temperature range, but still depends on the approximation of heat capacity ratio being independent of temperature, and for this reason will fail, particularly at higher temperatures. It gives good predictions in relatively dry, cold, low-pressure conditions, such as the Earth's stratosphere. The equation fails at extremely low pressures and short wavelengths, due to dependence on the assumption that the wavelength of the sound in the gas is much longer than the average mean free path between gas-molecule collisions. A derivation of these equations will be given in the following section. A graph comparing results of the two equations is at right, using the slightly different value of 331.5 ams for the speed of sound at 0 degrees Celsius. Details: speed in ideal gases and in air. For a gas, K is approximately given by. Thus, from the Newton-Laplace equation above. Where is the adiabatic index, also known as the isentropic expansion factor? It is the ratio of specific heats of a gas at a constant pressure to a gas at a constant volume, and arises because a classical sound wave induces an adiabatic compression, in which the heat of the compression does not have enough time to escape the pressure pulse, and thus contributes to the pressure induced by the compression. P is the pressure. Is the density, using the ideal gas law to replace with nRTV, and replacing I with nanometer per volt, the equation for an ideal gas becomes. Where is the speed of sound in an ideal gas? Is the molar gas constant? Is the Boltzmann constant? Is the adiabatic index, but none into vibrational modes. Gamma is actually experimentally measured over a range from 1.3991 to 1.403 at 0 degrees Celsius, for air. Gamma is assumed from kinetic theory to be exactly 5/3 equals 1.6667 for monatomic gases such as noble gases. Is the absolute temperature in Kelvin? Is the molar mass in kilograms per mole? The mean molar mass for dry air is about 0.0289645 a kilogram per mole. Is the mass of a single molecule in kilograms? This equation applies only when the sound wave is a small perturbation on the ambient condition, and the certain other noted conditions are fulfilled, as noted below. Calculated values for have been found to vary slightly from experimentally determined values. Newton famously considered the speed of sound before most of the development of thermodynamics and so incorrectly used isothermal calculations instead of adiabatic. His result was missing the factor of but was otherwise correct. Numerical substitution of the above values gives the ideal gas approximation of sound velocity for gases, which is accurate at relatively low gas pressures and densities. Also, for diatomic gases the use of requires that the gas exist in a temperature range high enough that rotational heat capacity is fully excited. But at the same time the temperature must be low enough that molecular vibrational modes contribute no heat capacity. For air, these conditions are fulfilled at room temperature, and also temperatures considerably below room temperature. See the section on gases in specific heat capacity for a more complete discussion of this phenomenon. For air, we use a simplified symbol. Additionally, if temperatures in degrees Celsius, a degree Celsius, are to be used to calculate air speed in the region near 273 Kelvin, then Celsius temperature may be used. Then, for dry air, where is the temperature in degrees Celsius, a degree Celsius? Making the following numerical substitutions. Is the molar gas constant in Kelvin? Is the mean molar mass of air, in kg? And using the ideal diatomic gas value of, then. Using the first two terms of the Taylor expansion. The derivation includes the first two equations given in the practical formula for dry air section above. Effects due to wind shear. The speed of sound varies with temperature. Since temperature and sound velocity normally decrease with increasing altitude, sound is refracted upward, away from listeners on the ground, creating an acoustic shadow at some distance from the source. Wind shear of 4 Mach/1 Mach/1 can produce refraction equal to a typical temperature lapse rate of 7.5 AA degree Celsius km. Higher values of wind gradient will refract sound downward towards the surface in the downwind direction, eliminating the acoustic shadow on the downwind side. This will increase the audibility of sounds downwind. This downwind refraction effect occurs because there is a wind gradient. The sound is not being carried along by the wind. For sound propagation, the exponential variation of wind speed with height can be defined as follows. Where equals speed of the wind at height, and is a constant, equals exponential coefficient based on ground surface roughness, typically between 0.08 and 0.52, equals expected wind gradient at height. In the 1862 American Civil War Battle of Iuka, an acoustic shadow, believed to have been enhanced by a northeast wind, kept two divisions of Union soldiers out of the battle, because they could not hear the sounds of battle only 10 km downwind. Tables, in the standard atmosphere, TO is 273.15 K, giving a theoretical value of 331.3 Mach/1. Values ranging from 331.3–331.6 may be found in reference literature, however. T20 is 293.15 K, giving a value of 343.2 Mach/1. T25 is 298.15 K, giving a value of 346.1 Mach/1. In fact, assuming an ideal gas, the speed of sound c depends on temperature only, not on the pressure or density. Air is almost an ideal gas. The temperature of the air varies with altitude, giving the following variations in the speed of sound using the standard atmosphere. Actual conditions may vary. Given normal atmospheric conditions, the temperature, and thus speed of sound, varies with altitude, effect of frequency and gas composition, general physical considerations. The medium in which a sound wave is traveling does not always respond adiabatically, and as a result the speed of sound can vary with frequency. The limitations of the concept of speed of sound due to extreme attenuation are also of concern. The attenuation which exists at sea level for high frequencies applies to successively lower frequencies as atmospheric pressure decreases, or as the mean free path increases. For this reason, the concept of speed of sound progressively loses its range of applicability at high altitudes. The standard equations for the speed of sound apply with reasonable accuracy only to situations in which the wavelength of the sound wave is considerably longer than the mean free path of molecules in a gas. The molecular composition of the gas contributes both as the mass of the molecules, and their heat capacities, and so both have an influence on speed of sound. In general, at the same molecular mass, monatomic gases have slightly higher sound speeds because they have a higher than diatomics do. Thus, at the same molecular mass, the sound speed of a monatomic gas goes up by a factor of equals 1.091. This gives the 9% difference, and would be a typical ratio for sound speeds at room temperature in helium versus deuterium, each with a molecular weight of 4. Sound travels faster in helium than deuterium because adiabatic compression heats helium more, since the helium molecules can store heat energy from compression only in translation, but not rotation. Thus helium molecules travel faster in a sound wave and transmit sound faster. Note that in this example we have assumed that temperature is low enough that heat capacities are not influenced by molecular vibration. However, vibrational modes simply cause gammas which decrease toward 1, since vibration modes in a polyatomic gas gives the gas additional ways to store heat which do not affect temperature, and thus do not affect molecular velocity and sound velocity. Thus, the effect of higher temperatures and vibrational heat capacity acts to increase the difference between sound speed in monatomic versus polyatomic molecules, with the speed remaining greater in monatomics. Practical application to air: by far the most important factor influencing the speed of sound in air is temperature. The speed is proportional to the square root of the absolute temperature, giving an increase of about 0.6 meters per second per degree Celsius. For this reason, the pitch of a musical wind instrument increases as its temperature increases. The speed of sound is raised by humidity but decreased by carbon dioxide. The difference between 0% and 100% humidity is about 1.5 meters per second at standard pressure and temperature, but the size of the humidity effect increases dramatically with temperature. The carbon dioxide content of air is not fixed, due to both carbon pollution and human breath. The dependence on frequency and pressure are normally insignificant in practical applications. In dry air, the speed of sound increases by about 0.1 meters per second as the frequency rises from 10 Hz to 100 Hz. For audible frequencies above 100 Hz it is relatively constant. Standard values of the speed of sound are quoted in the limit of low frequencies, where the wavelength is large compared to the mean free path. Mach number. Mach number, a useful quantity in aerodynamics, is the ratio of air speed to the local speed of sound. At altitude, for reasons explained, Mach number is a function of temperature. Aircraft flight instruments, however, operate using pressure differential to compute Mach number, not temperature. The assumption is that a particular pressure represents a particular altitude and, therefore, a standard temperature. Aircraft flight instruments need to operate this way because the stagnation pressure sensed by a pitot tube is dependent on altitude as well as speed. Experimental methods. A range of different methods exist for the measurement of sound in air. The earliest reasonably accurate estimate of the speed of sound in air was made by William Derham, and acknowledged by Isaac Newton. Derham had a telescope at the top of the tower of the Church of St. Lawrence in Upminster, England. On a calm day, a synchronized pocket watch would be given to an assistant who would fire a shotgun at a predetermined time from a conspicuous point some miles away, across the countryside. This could be confirmed by telescope. He then measured the interval between seeing gun smoke and arrival of the noise using a half-second pendulum. The distance from where the gun was fired was found by triangulation, and simple division provided velocity. Lastly, by making many observations, using a range of different distances, the inaccuracy of the half-second pendulum could be averaged out, giving his final estimate of the speed of sound. Modern stopwatches enable this method to be used today over distances as short as 400 meters, and not needing something as loud as a shotgun. Single-shot timing methods. The simplest concept is the measurement made using 2 microphones and a fast recording device such as a digital storage scope. This method uses the following idea. If a sound source and 2 microphones are arranged in a straight line, with the sound source at one end, then the following can be measured. 1. The distance between the microphones, called microphone basis. 2. The time of arrival between the signals reaching the different microphones, then V equals X/T. Other methods In these methods the time measurement has been replaced by a measurement of the inverse of time. Kuhn's tube is an example of an experiment which can be used to measure the speed of sound in a small volume. It has the advantage of being able to measure the speed of sound in any gas. This method uses a powder to make the nodes and antinodes visible to the human eye. This is an example of a compact experimental setup. A tuning fork can be held near the mouth of a long pipe which is dipping into a barrel of water. In this system it is the case that the pipe can be brought to resonance if the length of the air column in the pipe is equal to where n is an integer. As the antinodal point for the pipe at the open end is slightly outside the mouth of the pipe, it is best to find two or more points of resonance and then measure half a wavelength between these. Here it is the case that V equals V. High precision measurements in air. The effect from impurities can be significant when making high precision measurements. Chemical desiccants can be used to dry the air, but will in turn contaminate the sample. The air can be dried cryogenically, but this has the effect of removing the carbon dioxide as well. Therefore many high precision measurements are performed with air free of carbon dioxide rather than with natural air. A 2002 review found that a 1963 measurement by Smith and Harlow using a cylindrical resonator gave the most probable value of the standard sound speed to date. The experiment was done with air from which the carbon dioxide had been removed, but the result was then corrected for this effect so as to be applicable to real air. The experiments were done at 30 degrees Celsius but corrected for temperature in order to report them at 0 degrees Celsius. The result was 331.45 A plus or minus 0.01 meters per second for dry air at STP, for frequencies from 93 Hz to 1500 Hz, non-gaseous media, speed of sound in solids, three-dimensional solids. In a solid, there is a non-zero stiffness both for volumetric and shear deformations. Hence, it is possible to generate sound waves with different velocities dependent on the deformation mode. Sound waves generating volumetric deformations and shear deformations are called longitudinal waves and shear waves, respectively. In earthquakes, the corresponding seismic waves are called P waves and S waves, respectively. The sound velocities of these two types of waves propagating in a homogeneous three-dimensional solid are respectively given by where K and G are the bulk modulus and shear modulus of the elastic materials, respectively. Y is the Young's modulus, is the density, and is Poisson's ratio. The last quantity is not an independent one, as note that the speed of longitudinal compression waves depends both on the compression and shear resistance properties of the material, while the speed of shear waves depends on the shear properties only. Typically, compression or P waves travel faster in materials than do shear waves. And in earthquakes this is the reason that the onset of an earthquake is often preceded by a quick upward-downward shock, before arrival of waves that produce a side-to-side motion. For example, for a typical steel alloy, K equals 170 GPa, G equals 80 GPa and equals 7700 a kilogram per meter 3, yielding a longitudinal velocity CL of 6000 ams. This is in reasonable agreement with CL equals 5930 ams measured experimentally for a type of steel. The shear velocity CS is estimated at 3200 ams using the same numbers. Long rods, the speed of sound for longitudinal waves in stiff materials such as metals is sometimes given for long, thin rods of the material in question, in which the speed is easier to measure. In rods where their diameter is shorter than a wavelength, the speed of pure longitudinal waves may be simplified and is given by. This is similar to the expression for shear waves, save that Young's modulus replaces the shear modulus. This speed of sound for longitudinal waves in long, thin rods will always be slightly less than the 3D, longitudinal wave speed in anisotropic materials, and the ratio of the speeds in the two different types of objects depends on Poisson's ratio for the material. Speed of sound in liquids, in a fluid the only non-zero stiffness is to volumetric deformation. Hence the speed of sound in a fluid is given by where K is the bulk modulus of the fluid. This value typically decreases with temperature for non-polar fluids, The speed of sound in ultra-wave frequency range is inverse proportional to the cube of the volume of a fixed amount of the fluid. Water. In fresh water, sound travels at about 1497 ams at 25 degrees Celsius. See technical guides, speed of sound in pure water for an online calculator. Applications of underwater sound can be found in sonar, acoustic communication and acoustical oceanography. See Discovery of sound in the sea for other examples of the uses of sound in the ocean. Seawater. In salt water that is free of air bubbles or suspended sediment, sound travels at about 1560 ams. The speed of sound in seawater depends on pressure, temperature, and salinity, and empirical equations have been derived to accurately calculate sound speed from these variables. Other factors affecting sound speed are minor. Since temperature decreases with depth while pressure and generally salinity increase, the profile of sound speed with depth generally shows a characteristic curve which decreases to a minimum at a depth of several hundred meters, then increases again with increasing depth. For more information see Dusha al. A simple empirical equation for the speed of sound in sea water with reasonable accuracy for the world's oceans is due to Mackenzie, C, T, S, Z, equals A1 plus A2T plus A3T2 plus A4T3 plus A5, S, 35, plus A6Z plus A7Z2 plus A8T, S, 35, plus A9TZ3, where T, S, and Z are temperature in degrees Celsius, salinity in parts per thousand and depth in meters, respectively. The constants A1, A2, A9 are, A1 equals A1448.96, A2 equals A4.591, A3 equals A-5.304A, 10-2, A4 equals A2.374A, 10-4, A5 equals A1.340, A6 equals A1.630A, 10-2, A7 equals A1.675A, 10-7, A8 equals A-1.025A, 10-2, A9 equals A-7.139A, 10-13, with check value 1550.744 ams for T equals 25 AA degrees Celsius, S equals 35 parts per thousand, Z equals 1000 m. This equation has a standard error of 0.070 ams for salinity between 25 and 40 ppt. See technical guides, speed of sound in seawater for an online calculator. Other equations for sound speed in seawater are accurate over a wide range of conditions, but are far more complicated, for example, that by V. A. Del Grosso and the Chen-Millero-Lee equation. Speed in plasma. The speed of sound in a plasma for the common case that the electrons are hotter than the ions is given by the formula. Whereas the ion mass is the ratio of ion mass to proton mass. Is the electron temperature. Z is the charge state. K is Boltzmann's constant. K is wavelength. And is the adiabatic index. In contrast to a gas, the pressure and the density are provided by separate species, the pressure by the electrons and the density by the ions. The two are coupled through a fluctuating electric field. Gradients. When sound spreads out evenly in all directions in 3 dimensions, the intensity drops in proportion to the inverse square of the distance. However, in the ocean there is a layer called the deep sound channel or SOFAR channel which can confine sound waves at a particular depth. In the SOFAR channel, the speed of sound is lower than that in the layers above and below. Just as light waves will refract towards a region of higher index, sound waves will refract towards a region where their speed is reduced. The result is that sound gets confined in the layer, much the way light can be confined in a sheet of glass or optical fiber. Thus, the sound is confined in essentially 2 dimensions. In 2 dimensions the intensity drops in proportion to only the inverse of the distance. This allows waves to travel much further before being undetectably faint. A similar effect occurs in the atmosphere. Project Mogul successfully used this effect to detect a nuclear explosion at a considerable distance. See also, elastic wave, second sound, sonic boom, sound barrier, Underwater acoustics, vibrations, references. External links, calculation, speed of sound in air and the temperature, speed of sound, temperature matters, not air pressure, properties of the U.S. Standard Atmosphere 1976, The Speed of Sound, How to Measure the Speed of Sound in a Laboratory, teaching resource for 14 to 16 years on sound including speed of sound, technical guides, speed of sound in pure water, technical guides, speed of sound in seawater, did sound once travel at light speed? Acoustic properties of various materials including sound speed.